Hello everybody, welcome to more Google Lectures. I'm Ray and I would like to lecture on math20b midterm 1 today. Okay, the first thing I would like to cover today is integration by substitution. Let's begin with an easy example. This is an easy example where we need to use integration by substitution. And I think this one is pretty obvious to many who are good at this. Let's try this because we think this might work. And the derivative of u is 2x, and we have this in our integral. So we multiply this by 5 half, and we get 5x. So we know that 5x dx is 5 du over 2. Okay, so we can continue. Now this is a constant, so we can take it out of the integral. And this one is easy. We know that the integral of sine x, or sine u in this case, is negative cosine u times 5 over 2 plus constant. So let's substitute x squared back, and we will get this. Okay, so let's check let's check if we are correct. df over dx is and we can do this differentiation using the chain rule, which gives so we are correct. This is the basics of integration by substitution. So now let's move on to more examples. Sorry. Again, this one is pretty straightforward. Let's let u to be equal to log of x, the natural log of x, and du over dx is is 1 over x, so we can find out and this integral becomes note I have left out the limits from this integral. Why? Because this is very subtle and you must be careful when you use integration by substitution with definite integrals. If x is bound within these limits, what are the limits of u, which is equal to natural log of x? Here is 2 by definition, and here is 0 because the log of 1 is always 0. Now this is easy. Oh, sorry. Okay, now we still have a few examples to go. So you will probably know what would be wish to set u to be. Yes, square root of x and or because we have this dx over square root of x in the integral, we can, yeah. This is quite straightforward. So, again, be careful with the limits. The limits are no longer 4 and 9. They're 2 and 3, which are the square roots of 4 and 9, because u is equal to the square root of x. And we take negative 2 out of this integral. Now this is easy. Sorry. Hope you could see it. Because double negative here. Okay. Now, as you might see lots of trig integrals on the exam. Let's review the two basic trig integrals. This one is equal to negative cosine x plus constant. This one is equal to sine x plus constant. You won't have trouble with this if you're good at differentiation. But if you can't remember these, and if you're allowed to bring a cheat sheet to the exam, I recommend that you write down this on your. You should definitely write this down on your cheat sheet. Okay. Now let's move to the final example with integration by substitution. Now this one seems to have nothing to do with integration by substitution, and you might have no clue, but let's try this. Let's try this, because when you work with trig functions, you always want to reduce them to sine and cosine, because the derivative of sine is exactly the cosine function, and the derivative of the cosine function is negative sine. Let's try this. Okay. Now we get it. And we substitute the original function back for a reference. When you do indefinite integrals, you should never forget the constant, because if you don't include the constant, you might lose some points, and you don't want this to happen. Okay, great. Let's move on to the next part. The second part is integration by parts. Now, what is integration by parts? Basically, integration by parts is the integral version of the chain rule. It comes from the chain rule. The basic formula is here. To make it look more like B. I'm sorry. I was wrong a minute ago. It comes from the product rule. Let's try to derive this from the product rule. Although I don't think you would see a problem on the exam that asks you to prove this. You would be better off if you know the proof. Now? Now we integrate both sides, and the integral of this side is yes, we integrate both sides with respect to t. The integral of this side is simply ut bt in this side. And now this is pretty straightforward. So now let's see a few examples to see how we apply this. Example number 1. Okay, which one should we choose to be u, and which one should we choose to be derivative of v? Okay, we know that. So we think that choosing e to the x as v prime x might be the right choice. So let's give it a try. So v of x is also e to the x. Now let's plug it into the formula. And by the way, you should definitely have this formula on your cheat sheet, or you would be having a bad time, I suppose. Now, what is u prime x? U prime x is simply 1, so it's 1, we don't have to care about it. Here. What is this one? This one's probably easy, but if you don't remember this, try to memorize this. Sorry. Plus constant. Remember, whenever you're doing definite integrals, you can always leave the constant to the last step. This is how I usually do it. Now another one, which is more complex. Okay, this might seem pretty irrelevant, and you might find it really difficult. But how does it relate to integration by parts? It's really tricky. Now let's try integration by parts. We have two ways of doing this. Either u of t, we set u of t to be arctangent t, or we could set it to be 1. In this case, v prime of t is 1, and in this case, v prime of t is arc tangent t. And we will find this expression is worthless because it won't tell you anything valuable. You still don't know what v of t is. So let's stick with this one. V of t is equal to t, which is pretty straightforward. Okay, let's try. By the way, what is u prime t? You should have known this from differentiation. The derivative of arctangent is 1 over 1 plus t squared. Okay, let's begin. So let's continue with integration by parts. U of t times v of t minus v of t times u prime of t dt. What's v of t? What's u prime? U prime of t is this one, and so now what we have to do is this integral. If we find out this integral, we find out the whole integral. How do we do this? We can do this by substitution. Let's let u be 1 plus t squared, and du over dt is 2t dt. 2t, sorry. Du is 2t dt, and 1/2 du is t dt, which we have here. And here, u here, and 1/2 of du here. Okay. Okay. We take it out of the integral. This is a constant, and this is pretty commonplace. If you don't know this, although I think every one of you should know this. Okay, let's move on. Substitute back. Sorry, you might not see it. Okay, great. So we have this one. Okay. Okay, you could check this against the table of integrals, and I'm pretty sure this is correct. Okay, finally, a really complex one. Okay, this one is really complex. And intuitionally, we would do integration by parts. Sorry. Q of x equals prime of x. Let's say we want to do it like this. What is v of x? You can differentiate this to check if I'm correct. Yeah, I'm pretty sure this is correct. So let's move on. Sorry. U of x times v of x minus what's u prime of x, by the way. This is pretty easy. Minus u prime. Now, this is what we need for now. But how do we find this? To find this, we have to apply integration by parts again. Let's do the same thing. Let p of x be e to 2x and q prime of x be cosine 3x. Cosine of 3x. Q of x is 1/3 sine 3 times x. P prime of x e to 2x. Now, how do we do this? P prime x times q p prime x times q x dx. Okay. Let's simplify this once again. I'll use this side. We take all constants out of the integral. Okay, this. Sorry, minus. My fault. Now, we still don't have the answer, but you may recognize that this part is exactly I. So we have already obtained I implicitly, actually. I'm sorry, I messed up with the sign here, and now I'm right. Okay, if we want to know I, we multiply both sides by 9/5. This is easy. Okay. Or you may want it to be written more neatly. Difficult one, isn't it? But we have the answer now. So yeah, I think if you could do this, you have probably mastered integration by parts. So let's move on to the next part, finding area and volumes. Now let's start with the easy one. We want to find the area between f of x and g of x. First, we recall the formula. we're not sure of the sign because we need to know which function lies above which one. So we have g of x here and f of x here, I'm pretty sure. And next we need to find the limits, so we set f of x to g of x, and you can solve this by yourself, but I'll give out the answers. Wait. Oh, okay. Right. Clearly g of x lies above f of x. So how do we do this? The limits we have just calculated, and g of x minus f of x, because this is always positive and we want the area to be positive because the negative area makes no sense, right? What is g of x minus f of x? Okay. Easy algebra. Now this is quite easy. Okay, you can do this by yourself, and I'll give out the answer. 32/3. So what if we want to use polar coordinates? Theta. The point is, we have to know the lower and upper limits of this integral. Let's plug in. Okay, first you have to know how polar coordinates work. This is theta, and respectively this is r. This is how polar coordinates work. Okay, this graph is supposed to be symmetric over x, so we only need to find the area of this part. For this part, here and here, theta is either 0 or pi or 2 pi, which is equivalent to the 0. Okay, and at 0, distance from its point of origin is cosine 0, which is 1, 3. So here is 3, and here theta is 0, and here theta is pi. So in this case, we want to do 2 times, because remember this part? Remember this part, to find out the area of the whole thing, we have to multiply the area of this part by 2. 1/2 r squared d theta. Cancels out. R squared. Okay. Let's do this integral. We can expand the square. And you see cosine squared of theta. Remember this? Now we integrate term by term. What's the antiderivative of this one? Sine of 2 theta. This one, 2 sine theta, and this one. Easy. Okay, you can do this calculation on yourself, and I will give out the answer. Write it in. So these have 7 pi over 2. By the way, if you see cosine theta squared or sine theta squared, we use trig identities to transform them. Making integration easier. Okay, let's move on to volumes. Let's begin with the easy one. From 0 to 1. How do we revolve this around the x-axis? How do we calculate the volume of the solid generated? Well, an easy way to do so is to dissect it into infinitely many disks. Draw this even smaller. Of which is the thickness is dx and the height is y, and we revolve this around the x-axis, and this rectangle here will generate a disk. How do we calculate the volume of the disk? Pi times r squared radius, which is y, times dx. In this case, y squared is equal to x. So the volume is the integral of dv, which we know in turn is pi x dx from 0 to 1. Half of pi. So let's move on to another case, which is slightly more complicated but still manageable. Now we revolve this part around the x-axis, and this is not that straightforward, and we need to use not a ring, but not a disk, but a ring. And how to calculate the volume of the ring? Imagine a larger disk generated from this rectangle, and a smaller disk, let's use S, generated from this. Capital R and lowercase r. If you subtract the volume of the disk generated from this and the disk generated from this, you will get the volume of the ring generated from this, because like you. Imagine this is a disk. And we punch a hole into it. dV is equal to what is this? E to the negative x squared is e to the negative 2x dx. Okay, let's Move on. Volume is therefore we integrate in the term by term again. What is the antiderivative of this? By just observing, we can, pretty sure we could find this just by observing. Sorry. Again, I'll leave the calculations to yourself, and the answer though is okay, good. Well, sometimes, however, you would find it quite uncomfortable because you would have to integrate with respect to y, which is not the norm of what we usually do. Okay, suppose you would like to rotate S, rotate S around the y-axis instead of the x-axis. Doing this might be quite uncomfortable. We have to form a ring around a horizontal ring instead of the vertical one, and the thickness of the ring is no longer dx but dy, and again this lowercase r and uppercase r. We know that uppercase r is equal to 1 because it's always 1, independent of what x is and y is. But how do we find lowercase r? In terms of x, lowercase r is x, and which is in turn equal to the square root of y. So let's integrate with respect to y. Let's try it. R squared minus okay, it might seem complex and confusing at first, but now now we know it's not that difficult as we expected. So there's another type of problem involving volumes that you may encounter on an exam. Suppose that all cross sections, suppose that we generate a solid from the region here, S, so that all cross sections perpendicular to the x-axis are squares. Let's do this. Obviously, if all cross sections are squares, we can take thin slices from the solid, and they would be very thin. I would call it square cards, because the thickness is dx infinitesimal, and the area of the card is this squared. Sorry. Squared. Fx squared x 4 x is x. The volume is equal to oh, I'm sorry. My bad. This is supposed to be gx squared, gx minus fx squared. My bad. What's gx minus fx dx? That's equal to, this notation might be easier. Wait. Did I do something wrong? Sorry. Let's go back and check. Oh, this is exactly what I've done. I have done wrong, and I apologize for that. 9/70. Okay. Let's do an example from last year's midterm 1. Here, all of the cross sections that are perpendicular to the y-axis are semicircles. So we will have lots of semicircular cards of thickness dy, and how do we know the area though? The base area. This is the area of a semicircle, and what is it? Radius. The radius is half of this, so the radius is exactly half of this. Remember? Well, this part is square root y. And this part is equal to y. And let's expand this. Simplify. Okay, so dv will equal this times dy. We have to determine the limits of integration, and in this case that's easy because the lower limit is obviously 0, and the upper limit is obviously 1 for y. And we need to use the limits for y because we're integrating with respect to y. And things now become easy. Again, I'll skip calculations but the answer is pi over 240. Actually, I'm not sure about the correctness of the final numerical answer, but follow this procedure and try to not make mistakes in calculation. Oh, okay, no. Okay, so no, actually I would do this calculation. from like the value we want the value of this thing in the bracket when y is equal to 1 minus the value when y is equal to 0. Obviously, when y is equal to 0, this is all 0, so we only care about when y is 1. Okay, so this is correct. Okay, if we rotate this x around the x-axis, what is the volume of the resulting solid? According to our analysis of the examples, we can give out a formula This is a formula worth writing down on your cheat sheet. And what about this on the right? You will either rotate this around the x-axis or around the y-axis. If you rotate it around the x-axis, it's easy because it's simply this is just a special case of this formula, number 1 on the left, because in this case g of x is equal to 0. What if we want to rotate it around the y-axis? Now, what is big R? Big R is this, which is b, and small r is this, which we could write as f inverse y squared dy. And okay, and remember the limits are not a and b. It was my bad. The limits are f of a and f of b because we're integrating with respect to y, not x. You can also have this formula down on your cheat sheet. So okay, brief recap. The 4 things we went over today: substitution, integration by parts formula, again, if you're using this with definite integrals, just just add a pretty lower limit to everything, basically. Well, in any case, this means f of b minus f of a, no matter what is inside the brackets. Number 3, areas. The area between two curves are two curves is for this for 1. And I believe the most important and the arguably most difficult part is volumes. But volumes can just be reduced to 2 cases. Case 1, case 1, rotated. The volume of the solid generated from rotating s around the x-axis is equal to integral a to b f of x squared minus g of x squared times dx and if we want to rotate r around the y-axis, we will have integral f of a to f of b by b squared minus okay, so these are the 4 more important formulas. Of course, if they ask you to find, if you're asked to find the volume of a cross-sectional solid, it's more difficult, but still doable. Just use or and A will depend because like if the cross section is a square, A will equal f of x minus g of x squared. If it's a semicircle, A will equal 1/8 pi If you're, however, if the cross sections are perpendicular to the y-axis instead of the x-axis, it would be slightly more complex. But if you integrate with respect to y and express the length of this segment in terms of y, you would be fine. So that's all for today, and hope you do well on your first midterm. Thank you.